Your text is already in Parquet, but search still needs another server. DuckDB's FTS extension builds a local BM25 index and returns ranked matches in one Python workflow. You'll see how to connect the pieces into a workflow that rebuilds a local text index and ranks matching documents. I'm Professor Pi, teaching search and IR with simple Python. Full text search often splits into two teams. One team writes columnar data, and another runs a separate search engine. That split adds latency, operational overhead, and data sync problems. If your documents already live as Parquet files, you can avoid that extra service by running Retrieval where the data lives. The result is fewer moving parts and faster iteration when you need ranked context for a model or an app. At a high level, BM25 gives a relevant score for keyword queries. It favors terms that are informative and penalizes long documents. DuckDB exposes a full text search extension that implements BM25 and keeps everything inside a single embedded database. That is handy for prototypes and moderate-scale datasets where you want tight integration with SQL and Python. In plain terms, we will load a few documents into Parquet, open DuckDB, create an FTS index, run a BM25 ranked query, and then show how to keep that index fresh after adding new rows. Finally, we will wrap the query logic into a small retriever function you can call from a RAG flow. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, open DuckDB and enable the FTS extension, so this process can do ranking without an external server. This snippet opens a local DuckDB connection and loads the FTS extension. Before touching Parquet or ranking, you want the smallest possible proof that the embedded database can run SQL and expose extension features in the same Python process. The con object becomes the shared handle for the rest of the tutorial, so later steps do not need a separate search server, client pool, or export path. Con install extension, FTS, and con load extension, FTS, are the key DuckDB calls here. The output shows the connection is live, which matters because every later BM25 query runs through this same con. With the database ready, load some text into Parquet and read it back through DuckDB so the data path matches a real pipeline. This example turns a few readable documents into Parquet and loads them back into DuckDB. Teams often already have text sitting in columnar files, so the important move is keeping that data local instead of shipping it into a separate keyword engine. Copy seed to writes the Parquet file, and the next, create or replace table docs, reads that Parquet data straight back through DuckDB SQL. The ID column is the stable document key that the FTS index will use. The output confirms 4 Parquet rows are now queryable in docs, which matters before building the index. Now build the FTS index so matches are scored and returned in ranked order, not just found or missed. This snippet builds the DuckDB FTS index and asks BM25 for ranked keyword hits. Plain SQL filters can tell you whether text contains a token, but retrieval systems need ordering when many rows match. Pragma, create FTS index, indexes body using ID as the document key, and FTS main docs match BM25 returns a score for the query terms. Rows with no match are removed with score is not null. Then the results are sorted by score and ID for stable output. The output shows the top-ranked document ID, which matters because ranking is now happening inside DuckDB. Indexes aren't magical. They need maintenance after data changes. The next bit makes that explicit so fresh rows don't silently disappear from search results. This code demonstrates the DuckDB FTS rebuild requirement after writing new text. The sharp edge is that a normal table insert does not automatically refresh the full text index, so a fresh document can be invisible to match BM25. The snippet inserts D5, checks the stale index, then uses pragma drop FTS index, followed by pragma create FTS index to rebuild. That rebuild is the maintenance step you would schedule after a batch load or controlled refresh. The output shows the new row needed a rebuild and then became indexed, which matters for avoiding silent relevance failures. Finally, wrap the ranked query into a small retriever function so other parts of your pipeline can call it cleanly. This code wraps DuckDB BM25 search into a small retriever shape you can call from a RAG or hybrid pipeline. The useful baseline is not a demo query by itself, but a function that takes Q, applies a top T, and returns ranked context rows with scores still available. Search keeps the SQL parameterized, uses match BM25 for scoring, and limits the result set before Python receives it. Raising top K gives downstream re-rankers or generators more recall, while lowering it reduces prompt size and local work. The output shows the selected context IDs, which matters because this is the handoff point to the next retrieval stage. To connect this to a real project, imagine a customer support FAQ stored as Parquet. Swap in your FAQ table, run the same index and search flow, and hand the top context to a response generator. The same rebuild step becomes an automated job after nightly syncs. We did 3 practical things. Ran BM25 inside DuckDB so search lives with Parquet. Showed how to index and rank results with match BM25. And demonstrated the explicit rebuild step after bulk updates so you don't miss new documents. A useful next step is to tune the BM25 parameters K1 and B for your corpus. Try adjusting BM25 K1B to shift how term frequency and document length affect scores, and measure whether your top results match human judgments on a small validation set. If short, practical IR helps, subscribe and watch the IR videos.